Constant velocity, Lab 1. The purpose of this lab is to observe the motion of an object that is moving at the same speed without changing direction. The purpose of this video will be to report on observations and the model and the comparison between the model and observations. This video will also discuss the main assumptions made in the model to obtain good agreement with observations. What you have just witnessed is a Campbell soup can rolling across a flat surface at a constant velocity. We have just captured a video of motion. Now, we will analyze the video using Tracker to extract the object's position and corresponding time, construct a computational model that accurately describes observation based on physics principles such as Newton's law, equivalently the momentum principle, then compare the model to observations using position versus time graph for the predicted position and the observed position. This video will also address questions such as, what if? When using Tracker, you can plot the axes. I have used the plot to the left to be negative, the plot to the right to be positive. By switching these axes, now moving in the right is negative and moving to the left is now positive velocity. What does all of this mean? It means that we can affect our velocity by our graphs. So what of net force? Zero net force means that we have an acceleration of 0. This is due to our constant velocity. So, we've used Tracker to calculate the center of mass. By positioning the center of mass of the can, we can use this in later predictions. Our predictions, or our predicted ending position, we've used kinematics. Kinematic equations such as delta position over delta time to calculate the initial velocity. In this case, our initial velocity is negative because our can is moving to the left. So, Tracker also demonstrates a graph and data points, position versus time, and data points listed to the left of the screen. For our computational model, we used Python. Using a template and editing information to pertain to the specific data, a computational model was created to predict calculated values. This data was then exported into an Excel spreadsheet where we can see our observed versus our predicted final positions. Then, these were added to a graph to better display the predicted versus the observed final positions. Some sources of error in these positions were the assumptions made at the beginning concerning our net force. For example, resistive forces take part in impacting our predicted values because in the real world there are resistive forces such as friction, ridges in the can, and the carpeting. These are some of the examples of resistive forces that affected our overall final position and its exactness.